Okay, yeah, thank you very much for giving me the opportunity to present here something. So the model that I have in mind that I would like to understand in future is the following. It is a Markovian time continuous particle model with correlation in some box, if you like, to cross n. So particles belong have now a certain look. So a particle has a location x and the mass m, and the masses m are positive integers. At the beginning, all the masses are equal to 1, and I have precisely n particles. And in my notation, I order the particles according to the size of the mark. The size of the mass, m1 of t is always the largest one. And the last one, mnt of t is the last, the smallest one, large equal to 1. Small n of t is the number of particles at time t, and this is a decreasing function of t. Think of the axis as something like a location in space, and I would like to indicate with a lambda that the space does not depend on n. In this sense, I am talking about the hydrodynamic limit because n particles are present to one single box. The lambda can also be decorated with anything that you like to, for example, with an independent mark. You can give some RID random variable to each xi if you like to. And the dynamics is the following. So if you have a particle x comma m, and y comma n, which means at the space points x and y and having size m and n. Then you replace it at rate of a certain correlation kernel. So kn is now given. This is a collection of positive numbers. You replace it by one particle at this place here with a mass which sums the two masses of the particles. And the place is some convex combination of the two places where the two were in such a way that you have the same center of mass for these two particles, which means also the same center of mass for the entire particle system. So this is a model which we would like to understand. I forgot to mention all correlations occur independently, of course. The questions that we would like to ask is the following. So we would like to have a very comprehensive approach. We would like to first understand the joint distribution of all particles at time t for fixed t and for fixed n. And then we would like to make n to infinity for fixed t and see whether we can prove a large deviation principle for their statistics, by which I mean I just count how many particles of a given size at a given space point we have. Do we have an explicit rate function, and can we then analyze the minimizers explicitly? Yes or no? This is these are our questions. And then we have in particular law of large numbers of the configuration at time t as n to infinity towards the minimizers of the rate function. And we are most interested in phase transitions, so-called dilation phase transitions, which means appearance of a giant particle, so some particle such that the size of it is of order n, after some dilation time, which hopefully is positive and fine. In this talk, however, I will go to something simpler because it's a bit cumbersome to keep track of all the changes of the locations of the particles. For each single coagulation event, you have a change of the location of two particles. It's not a movement, no? It's just a replacement of two particles by one. And this is very nasty to keep track of this mathematically. So therefore, we went to some more modest goal. For this talk, I just do the following. Instead of true correlation, I just put a bond, which means I leave the particles at the same place as they were initially. And I just indicate that these and that two particles have been coagulated by putting a bond, which means, of course, that I have nothing else but a random graph. A random graph, which is where the particles have types. And therefore, the model that is suitable for explaining what happens here will later be the inhomogeneous Erd H random graph. So what I'm going to show you in the next couple of minutes is more or less something about the distribution, the joint distribution of all the components of an inhomogeneous Erd H graph embedded into time. So this is my plan for this talk today.
Where do you put the bond? You have streamlines, for example, 2 or something.
Yeah, for example, if I have 5 particles of that type, I put them on top of each other. and something like this. So I have 3 types, for example. This 5 particles have this type, 4 particles have this type, 3 particles have this type. I number them, of course. Each particle knows who it is. Yeah. So these are the numbers 1 to 12. Yeah. And now I put bonds between the indices, or between the particles. For example, this bond will be creating sometime. And another time, this will be created, this one will be created, this one will be created, and so on and so on. And this one here is, so to speak, a particle which has 1 atom, let me call it an atom of type of this type here, 2 atoms of this type, and 1 atom of this type here.
What's the type? Sorry.
Type is, so this is type A, this is type B, this is type C, and I have 5 particles of type A, 4 particles type B, and 3 particles of type C.
So, but the last bond that you have added, you could have added it to 4 to go to 4.
I could also, yeah, I could also include some bond like that here. So each of the bonds, so later the building principle will be each pair of particles has the possibility to have a bond, and this bond appears at a certain random time. No more bonds are there in the game. Like the building principle of an Erd H graph in continuous time. I will come to the details, of course. But you see here already that a particle, for example, this particle here, yeah, so it's seen as a particle in my correlation system. This has a lot of information. So I need to know how many atoms, let me call, are there with respective types. So a particle will be a multi-index. So the Markus-Lushnikov model is a non-spatial mean field correlation model. So for non-spatial models, there are also a couple of papers from something like 10 years ago by Freidun, and he gives interesting criteria for having a gelation time and when the gelation time is. Unfortunately, we were not yet able to use these works for spatial models. At the moment, and also for this talk, we are concentrating now on the multiplicative kernel. So the kernel is now the product of the 2 masses divided by n. And for this particular choice of the kernel, our correlation model or random bond model is a time-dependent version of the well-known Erd H random graph model. So here there's no space. The space. So forget the axis for a while. Yeah. So this is just the standard Erd H graph. More precisely, if I take now the probability for having a connection like that, 1 minus e to the minus t over n. This is roughly t over n. So we are in the sparse Erd H graph. Then the vector of the sizes of the particles is in distribution equal to the vector of the sizes for the connected components. And this is what we would like to study. So I'm making now statements about the joint distribution of the component sizes of a standard Erd H graph with probability roughly t over n for fixed t. So the graph is always on the index set 1 to 1, 2, 3, 4, 5, and to n. Later we look at the spatial version. I introduced the notion of microscopic, mesoscopic, and macroscopic sizes. So microscopic is everything that is of finite order, does not depend on n. Macroscopic is something which is of order n, and mesoscopic is something in between, depending on n, going to infinity, but being much, much smaller than n. There are some forerunners of the LDP that I'm going to show you now. These are the 4 papers that I think that I should mention here. For certain quantities of the Erd H graph, there were these papers here giving already some large deviation statements. Neil O'Connell looked at the size of the largest component, which will be included also in our analysis, and the number of isolated points, which is also will also be a part of what we are going to show. These 3 guys have are more on the statistical mechanic side. They look at the free energy for a tilted version where you give weights to the number of components, and they show some connection to the Potts model. Bordenave and Caputo do a large deviation principle for the microscopic components, not only as a component, but even as a graph. So they keep track of where the bonds are in each microscopic component. By the way, we're forgetting about this information in our analysis. And Puchalski has a number of interesting LDP results. The number of components, the number of macroscopic components. So this is for me the first time that also the macroscopic components have been looked at, and the number of excess edges inside them. So the structure inside the macroscopic component as it concerns only the edges that you have additionally to those which make it connected. This is enormously different from what we are going to do. Okay, in order to formulate, still for the standard Erd graph, we introduce these two observables, I would like to say. This one, the my empirical measure, this looks at the microscopic sizes and is normalized like that. It is not a probability measure, but it is a measure of finite order. And in contrast, you take the same random variables. Right? The sum goes always from 1 to n. You have all your you have all your sizes in your empirical measure, but this one is macroscopic because it registers in the end only those ones which are of order n. Everything that is somehow too large goes to infinity and is not there in the measure in the limit anymore, evades to, this is a loss of mass. And everything that is too small, small O of n, evades via the point 0. So therefore, in the end, the left-hand side measure registers only the microscopic, the right-hand side, the macroscopic components. There might be something in between, by the way. A bit more notation. So both are normalized. So this quantity here for this object here, so if you take the sum over k times my of k, then you get 1 for each fixed n. But in the limit, of course, the sum loss of mass can be. So therefore, we look at arbitrary c, and c can be small equal to 1. So loss of mass is precisely the point that we're looking at. So when do we have loss of mass there? And the same with the macroscopic things. So this quantity here, if you apply it to this object here, gives you the total number of particles, which is n for fixed n. But in the limit n to infinity, certainly you can lose a lot. For example, both together, it looks as if they could have 1 from here and 1 from there. No, that's not possible. The particles have to make a decision. Some of them go to the micro, some of them go to the macro, and possibly an overshoot goes to the meso, which is not explicitly registered here. This one here, C lambda, if lambda is a collection of these numbers here, this is a non-continuous function of lambda, and analogically, this is also a non-continuous function that can lose mass. So this is our phase transition. If we're talking about phase transition, this is nothing but the well-known Erd H phase transition from the 60s, but now on the scale of large deviation. So this is our large deviation principle for the standard Erd H graph. It looks a bit heavy. Maybe look at the last line here. This is a simple explanation of what happens upstairs. So we look at the probability for what? For each k, you want to have, so this is a number of components of size k, and this should be n times lambda k for every k. And at the same time, you would like to have the number of components of size n times x for any x. And this is alpha of x. Alpha is a measure on 0, 1, and lambda is a sequence of numbers, of positive numbers. You would like to understand the joint distribution of microscopic and macroscopic components. Written like that here is a bit awkward because you should make for k some cutoff until which you require this, and you should also make here some cutoff for the size of x, for the size of x, and then it makes sense. So in order to make really sense in terms of the large deviation principle, you should be a bit more careful. But the idea is that you get that the probability runs like e to the minus n times the rate function, and the rate function is upstairs. I would say the most important point is this one here. This gives you the large deviations for the collection of the sizes of the microscopic components. You see a term lambda k log lambda k. This comes from combinatorics. And you see a term k factorial divided by k to the k minus 2. This comes from the probability that that k points in the Erd H graph are connected. This is an in the denominator you have some term which is reminiscent of the probability that a given k points in the Erd H graph are a connected graph. So this is how it comes about. These terms are similar for the macroscopic components, and these terms here in the end, they are only in order they express something like that all the macroscopic components and all the microscopic components pairwise are not connected. This has also to be expressed there somehow. The minimizers. The minimizers are these ones, explicit formulas. So this is a minimizer for the microscopic things. If you take now the joint rate function of the lambdas and the alphas, then you have for t smaller than 1 that the minimizer is, as it concerns the macroscopic stuff, empty. And that also concerns the microscopic stuff. You see here the explicit statistics with c equal to 1 of the number of microscopic components with the size k for every k. This is, of course, well known, this formula. But it comes out now, not via some branching process as usual, but it comes also as a minimizer of a certain large deviation rate function. For t larger than 1, the minimum has to be calculated like that here. So you first find a beta t like that, which satisfies this one here. And then you see that the macroscopic part of the minimizer is one particle with size 1 minus beta t in brackets times n. And everything else goes into practically the same distribution like that here, but now with 1 replaced by beta t. These formulas are known. So consequences for our purpose, Tc equal to 1 is the gelation phase transition time. Before times 1, all the sizes are microscopic and their statistics follow the Borel distribution, the simplest distribution that never appears in probability 1 lectures. I don't know why. And after time 1, there's precisely 1 macroscopic particle of size, this one here, and the rest is also Borel distributed with different parameter. You can write down these formulas also in terms of expectations of the joint, the total progeny of a certain branching process. But let me come now to also first some comments. Maybe you were missing equations. There is an equation. The equation is more than 100 years old. The Smoluchowski equation. This is a system of ODEs which expresses the lambda k, only the micro part, as a function of t. So the t derivative is, so here you see that 2 particles join together. You sum over all the possibilities, and this is the rate that they go together. And here you subtract the particles that are going out of the system. I mean, 2 particles are replaced by 1. No? So this is the 2 particles go together, and these are the two single particles which go out. This equation has a phase transition for our multiplicative kernel, and it does not tell you much more after time 1 about this. Unfortunately, there is a version, the Ferrari equation, which tells you also something about what happens after the phase transition. You can calculate that our minimizers satisfy this. Some historical remark, convergence of stochastic correlation processes towards these deterministic ODEs was expected for a long time, but the first rigorous rule was only given 42 years ago. Let's go now to the inhomogeneous Erd H graph. This is really our goal. No? So we have now a compact metric space S for the types. Many of my formulas will be only for a finite set S, but everything that I tell you is true for an arbitrary compact metric space. For example, box in RD, cross some mark space if you like to. Then there's a probability to measure mu on the type space. And there's a connectivity probability function. This is a positive, symmetric, irreducible kernel, irreducible with respect to mu. So assume that mu has support equal to S, otherwise you cut the overshoot away. and assume that kappa is everywhere positive, for example. Then you have irreducibility. We have also something for reducible cases, but now I don't want to talk about this. The vertex set is, as before, the set 1 to n, and you have a type vector, like in the picture here. No? So x of 1 is A, x of 2 is B, and so on and so on. And Gn is now the graph. You see here 1 over n times kappa. Gn is a graph having a bond Rj with probability kappa of xi, xj divided by n, independently over everything. This is the inhomogeneous random graph. This was introduced, in my opinion, at least the first serious results were done in a paper with 120 pages by Bollob, Janson and Riordan 15 years ago. And they derived sufficient and necessary criteria for the phase transition of the existence of a giant component. Yeah, by the way, also the following: if you go to this kernel now and want to see the process as a coagulation process, then you can also do it like that. It is something like a product kernel. Yeah. So here you sum over all pairs. This gives you, so to speak, the product form in the number of in the size of the particles. So let me recall what the Bollob, Janson, Riordan paper said. An important object is this operator upstairs. This is nothing but the operator with kernel kappa seen on an L2 space with measure mu. Mostly it will take mu equal to mu, but not always. And the sigma is now the L2 norm of this operator, basically the largest eigenvalue of this operator, and written like that here. It also depends strongly on mu, which is later put mostly equal to mu. And then the criteria is the following: if this number is small equal to 1, then the largest component has size small o of n, in fact, capital O of log n, as you know it from the usual Erd graph. And if sigma is strictly larger than 1, then it has size n times this number here where rho appears. And rho is defined analytically by this as the solution to this equation. You can give also some interpretation to it in terms of the multi-type branching process. So the multi-type branching process works as follows: each particle of type S, X, has offspring distribution, which is itself a Poisson point process, with intensity k of xy mu dx. So this is as a measure in y. So this is the multi-type branching process, which is behind the picture. This is the main tool of this work there. And the rho of x is, oh, I forgot it. What is, this is the distribution, the spatial distribution of the cluster, the largest cluster in the case that the giant cluster exists. The spatial distribution of the vertices. Rho of x is now in density. Yeah. Now, how do we formulate this stuff? So I formulated not only for S and finite set. So everything is also fine for an arbitrary compact set, but the notation is then a bit less easy to understand. So we assume recall the xi's are the types of particle I, and we assume that their empirical measure goes to mu, and the mu was the fixed probability measure on S. Now we look at the collection of the connected components of our graph, and eta of them are the vertex sets. So this is a multi-index. So eta of the component Ci tells you for every ABC how many particles of type A, how many particles of type B, and how many particles of type C are in this component. So it is a multi-index. And we look at the microscopic empirical measure, which is just the empirical measure of these components, the eta of components. Then we have, by the way, this equation for every n all the time. So Kr is the rth index of the multi-index K. Yeah. So this means here basically, if you sum over all components and look only how many particles you have in R, then you see, of course, it is the number of particles that you have in your system at R. Yeah. And the macroscopic one is the same with a slightly different rescaling. The 1/n from here goes to there. So only macroscopic sizes are looked at there. And then this has satisfies also something like this here. So for each r, you have such an equation. So in the limit n to infinity, they may go to strict smaller. The joint distribution can be written down explicitly. So the joint distribution of the number of particles of size k. K is K is multi-index. It's not a size anymore. No, yeah, and this is equal to first some combinatorial term which tells you the number of possibilities how to decompose everything into so and so many particles with these and that types. Then you have here some combinatorial terms still from the number of times to decompose it, and then you have here the probability that the particle cloud with k as a multi-index is connected. Pn of k is just a probability to be connected in your running graph, and you have it lk times because you have lk such components. And this term here is now taking the product for any different pairs. Summarizing, this one is the probability that every two different components are not connected. Yeah, 1 minus kappa divided by n is the probability of not connected. And here's the number of times that you have this, the number of pairs of components. So it's relatively easy, but still explicit. We need the asymptotics for the connection probability. So Pn of k as n goes to infinity for fixed k runs like this here, n to the 1 minus the number of particles in this multi-component times the number tau of k, which is this one here. So here you take the sum over all spanning trees, and these are the spanning trees of the multi-type process. Yeah. And then you go over all the edges in your spanning tree of the kappa values. So this is a nice quantity which tells you the probability of being connected. You have to sum over all trees. And why only trees? Because you have always a 1/n for each edge. So you need to have the cheapest way of producing a connection, and the cheapest ways are trees. And for each tree, you get a factor 1/n out, and this is the number of bonds in your tree. Easy to understand. And I think of independent interest is the large deviation statement for the connectivity probability for macroscopic components. So y is itself a multi-index, and you take now n times y, because this means you take a macro component with a specific number of particles of given types. And the exponential rate of this probability is equal to this one here. Relatively simple formula. I think this is not in the literature about Erd H graphs so far. The difficulty in proving this is if you have two giant components, then you can easily make one out of it by just adding one single bond. This is, it's a bit annoying, but it's truth. No? Yeah, and this, nobody sees this on an exponential scale. Okay, this is now the large deviation principle for the multi-type version. Yeah, again, yeah, what can I say? There are lots of terms. I would say this one is still the most important one. So it is of the same form. So the lambda k log lambda k tells you there are some combinatorics behind it, okay? And here downstairs you see you see somehow roughly the Poisson point process with mu, with parameter mu, multi-index parameter mu, multiplied with the probability that this Poisson point process is connected. The normalization is somewhere else. Yeah. So roughly what you see here is a kind of entropy between your collection of point processes with respect to a Poisson point process with multi-indices mu(s). So maybe this is a good interpretation of it. You have something similar here as well for the macroscopic components. And all the terms with 1/2 come from the non-connectedness of any pairs. of anything. And you see that we have also a mesoscopic function, which is not particle-wise, but altogether we have to put all the mesoscopic components together because we cannot go to all these continuum of scales, of course. We can only summarize all the mesoscopic stuff, and it has a non-trivial large deviation function. Some remarks. So for discrete S, this is combinatorics. If you want to go to continuous S, this is a cumbersome and technical work, and we use the Dawson-Gardner theorem. And this is really some technical stuff. It took us a long time. Thirdly, you can do the following. You can take the types x1 to xn itself as IID random, or as placement, or some IID marks if you like to. Then you get a quenched large deviation principle via our LDP. There are annealed versions which you can easily get by adding now the expectation over the axis and adding some entropy term for the effective distribution of the axis, if you like to. There are standard consequences for the microscopic part and the macroscopic part alone each. If I find time, then I can show you also an interesting conditional phase transition. And here's now the Ferrari equation that follows from it. If you take now the kernel, depending on t like that here, so the t parameter is this one there. So if t is increased, then you throw more and more particles in. So this is now the increasing process of multi-type Erd H enyigraph, which you can embed easily into a Markov process in continuous time. Yeah. And then the corresponding minimizers, which I have not yet written down, the corresponding minimizers as a function of t satisfy this equation called the Ferrari equation. And you see somehow that the first two terms on the right-hand side are the same as for the Smolov-Hofsky equation. But then you have an additional thing which somehow tells you something about the loss of mass between time 0 and time t. So at the beginning, this term is equal to 0, and you don't see it. But at the gelation time, this term is then non-trivial and gives you some information about how quickly the mass runs away. So we can show for our minimizers that they satisfy this. Yeah, the discussion of the minimizer, I'm a bit faster now. So you have to write down the Euler-Lagrange equations. So this is the formula for a possible minimizer. Possible minimizer, if you fix now somehow how many particles per type you have. The only candidate for this Euler-Lagrange parameter is this one here. And you call the solution lambda star of C if it exists. But you have to make an additional minimization over all possible C. C is just a measure, or is something which is pointwise below the mu that I plugged in. And I have to optimize also over the C. So therefore, it's similar. It's very analogous what I showed you 20 minutes ago. And here it is something about multi-type power series. T of C, this one here, is a solution if and only if the map T itself is invertible and the inverse map is analytic. So we are choosing a way which has much to do with inversion of power series. And this invertibility is true if and only if the corresponding sigma, the one from the paper by Bollob and so on, is strictly smaller than 1. And summarizing then the following: if the number is smaller or equal to 1, then this minimizer can be defined for C equal to mu, and it is the minimizing configuration, and the macroscopic stuff is empty. And by the way, this is the same. This is the one which Bollob and Ko had certainly in mind, could have also worked out, but after 120 pages, I think you don't want to add anything else. So they gave implicitly how to define in terms of multi-type process, but they didn't carry this out. And if sigma is larger than 1, then the optimal microscopic cluster distribution is characterized by this one here. And now the minimizer is this one here. So you have a delta measure in just one single configuration. And this is the mu minus the C star. The C star is characterized by this equation here. So mu minus C star is now the vertex distribution of the macroscopic cluster, and everything else goes into the microscopic distribution. It is this one there with C star. Here's a connection to the multi-type branching process. I jump over it and go to my favorite now to a phase transition. This is a phase transition which needs large deviations. So far I've done only law of large numbers, no? But this here is a conditional one, and this is something that you can do in terms of the large deviation rate function. So look at the macroscopic stuff. It satisfies the large deviation principle, which is equal to this one here. And the J is explicit, this is this one here. You see already here's a certain phase transition, but now with these parameters. No? What is the interpretation of this phase transition? So maybe it's a bit technical. Let's look at the conclusion. If you fix now the macroscopic stuff, so alpha is a configuration of everything that is macroscopic. So this is put. Yeah, so your condition on this. Now you go with your particles, you throw in your particles, make n to infinity, and throw in more particles, more particles, more particles. So there's a parameter which increases in the number of particles. And if the corresponding sigma, which is increasing in the number of particles, is smaller than 1, then you have just the microscopic distribution, and there's no mesoscopic part, by the way. And if you are going beyond the number, then you see that the corresponding lambda is a B star, and there is a non-trivial mesoscopic part, because this function, this explains only mesoscopic stuff here. This mesoscopic stuff is suddenly non-trivial, and this means there is some mesoscopic stuff really contributing to it. This is a saturation phase transition. If you fix the macroscopic part, put in more and more bonds, excuse me, not particles, I throw in bonds, excuse me, it's increasing in bonds, yeah. Then first, we have only increasing microscopic stuff and empty mesoscopic stuff. And later, until you have the critical configuration lambda B star attained, and if you throw in more bonds, then everything goes into a mesoscopic stuff. And this is what I call phase transition of saturation type, and it has also great similarities to what some people call frozen percolation. That's the end of my talk. Thank you very much.
Thanks, Wolfgang. Are there questions?
Just a curiosity, do you know if this true coagulation, so not the one with the bond, has something to do with this this condensation phenomena of the zero range process or the inclusion process, where all particles piles up on the same side?
I don't know what that has to do with this. Or I think I cannot say anything about this.
Yeah, Milton.
There's something I didn't get from your formulas. It's that whether in some cases some mass goes to the mesoscopic phase or not.
In some, the mesoscopic rate function is explicit, but it has the only minimum at 0, which means the law of large numbers tells you, as everybody knows, that mesoscopic stuff is not there with probability tending to 1. But you do have a non-trivial formula for the exponential probability of having some mesoscopic stuff.
Okay, thank you for this talk. When you say there is a mesoscopic part, can you tell what is the distribution of the mesoscopic?
The limiting distribution is 0. I mean, mesoscopic stuff does not exist in the limit, no? And not on the limit on the limit n. So I'm making assertions only on large n limit with prefactor n, and I can tell you the probability.
But but you see in your last slide,
this is a non-trivial term which tells you the probability that a positive percentage is somehow mesoscopic stuff.
No, but the mesoscopic has some, you see, there are all kinds of sizes.
Yeah, this is the difficulty. I have a continuum of scales, and I cannot pick out any kind of these scales. On the scale n, you will see only 0. But the totality of all the particles, strictly between 1 and n, so to speak, no? The totality, just the total number of them, this is something that has a large n limit, as a large n large deviations.
Are there other questions? Okay, if not, let's thanks again Wolfgang König, all the speakers of this morning.